Alright, hello everyone. This is going to be the final set of notes and the final set of video lectures covering sections 4.8 and 4.9, so this is going to wrap up the trigonometric section. And yeah, as I said in the update on Blackboard and I think CampusWire, or at least an email, I understand that you guys are not having homework for this set of notes, and that will be taken into consideration when I build the final on WebAssign. So I would encourage all of you to obviously watch these videos, work through the exercises in the notes on your own, maybe even open up the book, which I know you all have to have because you all have the registration thing for WebAssign, and just sort of familiarize yourself with these types of problems. Alright, that being said, let's just get going. So this section is mostly about inverse functions. Inverse of the trig functions, and so first let's just briefly review some facts about inverse functions. So if we recall, the only functions which have inverses are those which are one-to-one. So just a brief, a function f is going to be one-to-one if it passes the vertical and horizontal line tests. Right, so, forgive my handwriting, but an example of something which is a one-to-one function would be something like, no, not that, like x cubed. So this is going to be a one-to-one function because we can take any vertical line and we notice that it only ever intersects it at one point, which is great. And the same is true for any horizontal line. It only ever intersects it at one point. So x cubed is one-to-one because it passes both the vertical and horizontal line tests, but an example of a function which is not one-to-one is, surprise, surprise, sine and cosine. So here I'm just going to do the graph of cosine because it's a little bit easier, and you see that while it definitely passes the vertical line test, we can take any vertical line and it only ever touches it at one point. It is demonstrably not the case for horizontal lines. In fact, if any horizontal line touches the graph of sine or cosine in at least one spot, it has to do so infinitely. At infinitely many spots because it is periodic, right? So anywhere that a horizontal line touches it somewhere, it'll also touch it one period later, and another period later, and another ad infinitum. So sine and cosine are not one-to-one functions. However, well, first let's just keep talking about some of the properties of these functions, inverses. So this is all going to assume that f is one-to-one. So whatever function we're talking about, I'm going to call it f, and we're assuming it's one-to-one. So then f inverse is denoted as f to the negative first. I don't think that's big enough. F to the negative first, and this is going to be unique. Right? There's not going to be two different functions which will both undo the operation that f does. So yeah, it's unique. The domain of f inverse is the range of f, right? Because we are considering f inverse to be undoing whatever f did, and so that means that we have to take as inputs for f inverse the outputs of f. All that means is the outputs of f is exactly how we define the range of f. So if f inverse takes inputs, which are the outputs of f, then the domain of f inverse has to be the range of f. And vice versa, the range of f inverse is going to be the domain of f. Again, this is just because they flip the operation. I'm not going to write that one though because it's nearly the same. And then if f of x equals y, then f inverse of y will equal x. right? Again, this is just saying that the definition of the inverse function is one which undoes whatever the function did. So if f does something to x and turns it into y, well, y is now in the range of f, and so it's in the domain of f inverse, and so f inverse is going to take y and sort of reverse whatever happens to x to create y, and so it's going to produce x as an output. And then based on these two facts, or based on those, those two facts, we have that f of f inverse of y is going to be, well, f inverse of y is going to be some number x, and then f of x is going to be the exact same number y again, because these two are inverses. When we compose them together like this, they effectively do something and then undo that something immediately, so it doesn't do anything. Likewise, if we have f inverse of f of x, well, then f of x is going to do something to x, and then f inverse is going to undo that exact same thing. So this is also going to be just x. So basically, whenever you see a function composed with its inverse, it does nothing. It's called the identity function, or it just doesn't do anything. So with those, all right, the last thing, which isn't really going to be too important in a while, but helps with the very next part, is that f inverse and f are symmetric about the line y equals x, right? So this is that 45-degree line that is here. And so if we had some function that did, like that, then we would expect its inverse to essentially take the x term and switch it for a y term, right? Just as we said, f of x equals y, then f inverse of y equals x. Essentially, that is the primary operation that they're doing, is to flip which one you're considering the input and which one you're considering the output. And that amounts to essentially taking our xy coordinate system, and if this is x and this is the y-axis, essentially your inverse function is going to be plotting all of the exact same stuff, just mirrored along that line. And I know that's not perfectly mirrored, but it will essentially flip which one you consider x and y, which amounts to graphically as this mirror symmetry about the line y equals x, because that's the line which denotes that reflection. So, with that little review out of the way, if you're still confused about stuff like one-to-one, I would just say go back to whichever note section I cover that in. I think it's in chapter 3 somewhere. But yeah, so we are going to move on, and we are going to say, we noticed already that the trig functions sine and cosine, and indeed tangent, secant, cosecant, and cotangent are definitely not one-to-one. However, we can restrict their domain and range to where they are one-to-one, right? So if we look at the graph of sine, which is not that, if we look at the graph of sine, then we see that it starts repeating. Well, if we take sort of right here, all the way out to, where do I want to do this now? Let's not say that. I want to make it symmetric about the y-axis, so I'm going to take it from here to here. So if we notice, I put the next one here, we sort of get this S shape, and it repeats itself perfectly on all of these things. Like that's the period. The distance between these two is going to be 2 pi. However, if we look at this, if we restrict sine to be between negative pi and pi, right, so we're ignoring the rest of sine, and we're sort of saying pretend it only exists between negative pi to pi, we would get this. We would get exactly one of the sort of unit chunks of sine, which are repeated infinitely. However, what we want is a domain and range on which sine is 1 to 1, and that's still not true, right? I have both of these, right? Like this horizontal line is still going to contact this portion of sine in more than one spot, and so it's still not 1 to 1 because it still fails the horizontal line test. However, if we continue to sort of draw in the domain of this, then we can effectively say, well, the first place that it starts to repeat a value is sort of right here, right at the top of this curve, because the points just to the left of this curve will be lower, and the points just to the right of this apex of the curve will also be lower, and so they'll have the same value. So if we cut everything off at that peak, we get something which is no longer one of these unit chunks of sine, but this curve is 1 to 1. Right now, it still is going to pass the vertical line test, but now when we do the horizontal line test, we no longer have the same values sort of on the either side of that curve. And so this is going to be how we define the inverse of sine is on this domain, right? So we know that the inverse of a function is going to have the range and domain flipped from the original function, so what is the domain and range of this? This is essentially, I'm actually going to correct that to be the actual one. So the domain of this is going to be, well, we cut it off at the peak and the trough. And if we look at sine, the peak is going to be when sine of x equals 1, sort of the first time, which I actually call the primitive or the principal value. And so what is the first x value that does this? Well, it's going to be when x equals pi over 2. Because if we have the unit circle, sine is always the y value of these things. And so sine is going to be 1 exactly when sort of this triangle slims up to be just a vertical line, because the unit circle has radius 1, and so sine will be 1 whenever the sine is exactly the radius. And so that means it's going to be a 90-degree rotation, which is pi over 2. So we know that the principal value for sine of x equals 1 is going to be pi over 2, and so that is exactly what this value is. And symmetrically, we could also take sine and go down to negative pi over 2. So we have to restrict sine of x to be within this domain, and in this domain, sine of x is now a 1-to-1 function. But now what is the range of this function? Well, the range is actually not going to be changed. Originally, sine is bound between negative 1 and 1, because it equals 1 up here and it equals negative 1 down here. And since we still have the peak and the trough, which correspond to there and there, then we still have everything bound between negative 1 and 1. So this is the domain, and the range will be negative 1 to 1, sort of unchanged. And so because of this, we have, now we can start to define the inverse of sine. And there's actually two different ways to denote, sort of in symbols, what the inverse of sine is. The first way is to say sine to the negative 1 of x. And this is the exact same notation that I used in the recap and back in chapter 3, and pretty much everywhere, is whenever you see a function raised to the negative first, it doesn't mean 1 over that function, like raising to the negative first means with numbers. Instead, it means the inverse function. I actually made a whole point about why we have secant, cosecant, and cotangent instead of just 1 over them, because the raising to the negative first doesn't mean reciprocal, it means inverse. It's not very intuitive, but when you work with it long enough, you start to just, I don't even see it anymore. But this is one way to denote the inverse function for sine of x. There is another way which kind of circumvents this whole raising to the negative first anyway, and it's called the arc sine of x. And so these are two different ways to represent the inverse trig function for sine. In fact, this prefix arc, it comes from arc length, which is something that you can find using these inverse functions really easily. But this prefix will actually be used to denote all of the inverse trig functions. And I'm just going to go ahead and use that throughout both the notes and this lecture, just to dissuade any kind of confusion. So arc sine, so arc sine, its domain is going to be the range of sine, which is this thing. So its domain will be from -1 to 1, and its range will be the domain of this sine, which again is artificially given a domain between -π/2 and π/2. So this is going to have range of -π/2 to π/2. And if we want to look at what does arc sine actually look like as a graph, well, we don't need to look any further than using our 45 degrees symmetry, right? So I know that our arc sine is going to look like that, roughly. And in fact, one of the images I include in here has sort of the extended thing. So if we didn't artificially cap this, and in fact we had sine continue on, then the inverse sine would also continue on vertically. And with this, oh wow, yeah, I think you can see that. Okay, this is complicated and messy, and most definitely not one-to-one. And the problem with this is if I say, what is the output of this value in inverse of sine? Well, the principal value will be this, but it also gives you this and also gives you all of these other things as well as all of them below. So in order for us to have a unique and well-defined inverse function, we have to limit things. So we don't have this crazy infinite vertical squiggle. Instead, we have a very docile and controllable sort of kind of squiggle that comes from confining sine until it is 1-to-1 and then taking the inverse. Likewise, we have the same thing with cosine. So if we look at cosine, then it looks like this. And so we want to do the same thing. We want to find a domain on which cosine acts like a 1-to-1 function. And so we're going to do the exact same thing. We're going to sort of take it between a peak and a trough. And here's where cosine is a little bit different because it starts at 1 and then goes down, whereas sine starts at 0 and then goes up. We're not going to be able to find a domain that cosine is 1-to-1 over and symmetric about the origin. Instead, it's going to be sort of shifted off to the side. And because of that, its inverse is going to be slightly different looking as well. So this is actually the restricted domain for cosine, and just as it did for sine, because we put it between a peak and a trough, the same is true here. It is now 1-to-1. And so what is the domain of this is essentially asking what is the set of numbers that we can input here and still get a 1-to-1 cosine. It's going to be between 0 and the first time that cosine has its trough, which is -1 at pi. So the restricted domain for cosine on which it acts like a 1-to-1 function is from 0 to pi. And the range is the same as the range for sine, right? It's still bound between -1 and 1. And so this means that we can now take our 45-degree line and figure out what cosine's inverse would look like. And so, oh geez, what would this look like? It would look something like... Oh, I'm not even going to try to draw that. Yeah, so it's going to look something like that, and it's going to be... If we were to extend it this way, it would look like that, the same thing that we had with the sort of infinitely extended sine curve reflected, but now we can just cap it between these two values. And so it's going to be between here and here. And the rest of this is extraneous. We don't actually want that because that's going to make defining inverse of cosine even harder. So that does not seem like it follows the reflective thing, but in the notes I put a picture for cosine, and it does still. Yeah, so then we have the same thing. We have arc cosine of x, and its domain is going to be the range of cosine. So this is going to be from -1 to 1, and its range will be the domain of cosine, which is 0 to pi. And so we can start using these facts. Yes, the next one is, so the next one is, what is the inverse of tangent? Since tangent behaves slightly differently, tangent, I'll just draw a small little picture of tangent again. It looks like this. Right, with vertical asymptotes at each point that cosine is 0, which is going to be at pi over 2, 3 pi over 2, 5 pi over 2, and so on. So every time it's at the top or at the bottom, then the cosine, which is the x value, is going to be 0. And so at each of these points, we have a vertical asymptote. And so what this means is that well, obviously, this is definitely not 1-to-1. Again, it passes the vertical line test, but it very clearly fails the horizontal line test because that line's going to intersect at infinitely many points. And in fact, unlike sine and cosine, where we could sort of draw a line above or below the entirety of its graph, that's not true for tangent. Every horizontal line is going to intersect at infinitely many points. So, tangent is not bound normally. It goes from negative infinity all the way up to positive infinity. And so we're going to need to restrict things, but in a way it's less important. So we want sort of one of these things. I don't know, it's like a unit of tangent. It's the part that gets repeated over and over again. And it goes from negative pi over 2 to pi over 2 because that's where these asymptotes are. It's at those values that cosine is 0, and since tangent is sine over cosine, we have division by 0. So a single one of these curvy bits is going to be between negative pi over 2 to pi over 2. And on this domain, on this interval, tangent is now 1-to-1 because it passes the horizontal line test and the vertical line test. So its domain is going to be negative pi over 2 to pi over 2. And its range, well, it goes all the way up and all the way down. So in fact, its range is going to be negative infinity to infinity. And then when we look at the inverse of tangent, well, it's going to be this exact shape, just flipped about the 45-degree line, and so it looks like that. And you can probably see it better in the thing that I put in the notes. But again, we are going to denote this as arctangent, and the domain of arctangent is going to be from negative infinity to infinity because that was the range of tangent, and the range of arctan is going to be negative pi over 2 to pi over 2. And we can kind of see why that's true because on this arctan curve, the vertical asymptotes now become horizontal asymptotes, and we can see that this is going to sort of asymptotically approach pi over 2, but never get there. So the range is going to be sort of infinitely approaching pi over 2 and infinitely approaching negative pi over 2, but never actually getting to that. Yeah, so that's sort of, we understand that because sine cosine and tangent are periodic functions, that they are not one-to-one. And so in order for us to define an inverse of these functions, we have to artificially sort of ignore most of the graph and look at the part of the graph that is one-to-one. So those are the definitions, and we have to understand that the domain and ranges of these functions are now different. Okay. Yep. All right, so we see that the exact same things are true with inverse trig functions as with any inverse function. So if we have the cosine of the arc cosine of 5, well, we know that cosine and arc cosine are inverses of each other, so this is just going to be 5, right? And sort of arc cosine does something to the number 5, and then cosine does that exact thing in reverse and gives you back 5. Likewise, if we have, let's say, arc sine of pi over 2, well, this is going to give us sine of pi over 2 is going to be 1, and then the arc sine of 1, well, essentially what that's asking is what angle gave you a sine of a sine of 1. And obviously the answer to that, at least on the interval on which arc sine is defined, that answer is pi over 2. Right? So arc sine and sine are inverses of each other, so sine does something to pi over 2, and then arc sine undoes that very same thing to give you back pi over 2. And then we can have arctan of tangent of 1, and tangent of 1, that's going to be some number, and then arctan is essentially going to take that number and ask what angle gave you that number for tangent, which is of course 1, the number that we plugged in to get that number. So this is still going to be 1. These functions are all just going to undo each other, and so if you compose a function with its inverse, it does nothing. Okay, this fact is going to be useful when we start to do some of these examples. So the first example that I have in the notes is find cosine of arc sine of 3 over 7. So a little bit of preamble before we get into this. Effectively, when we say that arc sine takes this as an input, we remember that arc sine does the opposite of what sine does. Sine takes an angle on the unit circle and outputs the y value of the point on that circle. So if we have arc sine, the inverse of sine, what it should take is a y value and should output the angle which produced that y value on the unit circle. So when we see arc sine of 3 over 7, 3 over 7 is interpreted to be the y value of that point on the unit circle for some angle. Another way to think about this is, since sine of theta is opposite over hypotenuse, when we take arc sine of opposite over hypotenuse, it should give us theta, the angle. So, since we see arc sine of 3 over 7, it matches this type of description. Effectively, what arc sine, arc cosine, and arc tangent take as inputs, you can think of as ratios of the side lengths of a triangle. Ostensibly, that triangle is on the unit circle, but not necessarily. In fact, in this case, since we have arc sine of 3 over 7, that 3 must be the opposite side, and the 7 must be the hypotenuse for some triangle. So we can sort of draw that. Now, if this is our theta, then the opposite side is going to be 3 here, and the hypotenuse is going to be 7 here. And so, when we say the arc sine of 3 over 7, effectively what we are asking for is what is the angle that this triangle will have if it has side length 3 and hypotenuse 7 in this arrangement. You have to be very careful that because sine is defined as opposite over hypotenuse, you don't put the 3 here, because now that is actually adjacent over hypotenuse, which is cosine. So when building these triangle diagrams to help figure these things out, you have to be very careful about which one you label as what. But now that we have this triangle, it's going to be a relatively easy exercise to solve for this missing side length. We can use Pythagoras. We have that 7 squared is going to equal 3 squared plus x squared, if we call this side length x. And so x is going to be the square root of 49 minus 9, which is 40. So we can just write this as the square root of 40. So now we have all 3 side lengths of this triangle. We don't know what the angle theta is, but as we're about to see, we don't really need to, because arc sine of 3/7 gives us this angle. And then we're trying to find the cosine of that angle. So we don't really need to know what that angle is. Instead, we just need to know this triangle. So now the cosine of theta is going to be adjacent over hypotenuse. And so this is going to be the square root of 40 over 7. And this is the answer. When we look at I just lost my place. But yes, this is the correct answer because arc sine of 3 over 7 is talking about a triangle which looks like this, and then cosine is asking for one of the relationships between the side lengths of that triangle. So we don't actually need to know what the arctan of 3/7 is. All we need to know is how to translate that into a diagram from which we can find any of the other trig functions for that same angle. So let's do another one. So this concept of taking arc, cosine, or arc sine, or arc tangent and translating that into a triangle is a really powerful idea. If we have the next one, it is find arc tangent of sine of pi over 3. And in the notes, the code didn't really go through, so it says pi instead of pi, but you should all know what that means. So we know that sine takes angles as inputs. So pi over 3 in this case is representing an angle measure, not a side length. And so you might think, well, we don't have a ratio of things, and I don't know. How do we build a triangle from this when it gives us an angle instead of a ratio of sides? Well, we know how to take any angle and convert it into a triangle on the unit circle. So this part is actually talking about a triangle which looks like this, where here is, not theta, we know what it is, it's pi over 3, and the hypotenuse is 1, and this is the sine of pi over 3. This is just a triangle that you would take directly from the unit circle. So we know that this is root 3 over 2, and this is 1/2, just because of the stuff we've done in the previous set of notes. So this is now the triangle that we're talking about, and so now we can apply arctangent to this triangle, because they're talking about the same thing. Sine of pi over 3 is effectively this triangle, and then the arctangent is going to be talking about this. So yes. So effectively we can replace this as arctan of root 3 over 2, and now arctangent is again taking as its input a ratio of side lengths of a triangle, and so now we can say, all right, that one we got one triangle from, and now this we're going to get a different triangle from. This is going to be, so tangent is opposite over adjacent, TOA, yeah. So this guy has to be opposite over adjacent equals root 3 over 2. So the triangle that we have to draw is going to have, if this is theta, then the opposite side from theta has to be root 3, and the adjacent side to theta has to be 2. And so we can do similar things. So now we can figure out what the remaining side is by using Pythagoras. So root 3 squared is 3, and 2 squared is 4, so this is going to be the square root of 7. And unfortunately, this is where we will have to stop solving this by hand, because now to actually find the arctan of root 3 over 2 is to actually find what is this angle measure. And at least I don't know how to do that without going to a calculator. So you can go to the calculator, you can see that there's a tan to the negative first. It's probably in blue ink rather than the more prominent other one. You might have to hit second or function or whatever to enable these secondary buttons. But you can find this, and then you plug in root 3 over 2, and it outputs, what is it? It is approximately 0.7137 radians. And so we can try to figure out what that's close to, but it's not super important. The important part is that we understand how to take these types of problems, and even though arctan and sine are not inverses of each other, we can still interpret what this is saying, and we can still find an answer. All right, the next one is going to use both of these things sort of combined. So this one says, find, where is it, the cosine of the arc tan of 12 over 5 plus the arc sine of 3 over 5. Yes. And so this is kind of a beast. I wouldn't really want to work on this unless I had to, but I do. So the first thing we can say is this is a cosine, and it's a sum of two things inside of cosine, so we're going to use the angle sum formula for cosine. If we don't remember what that is, that's cosine of alpha plus beta is equal to cos alpha times cos beta minus sine alpha times sine beta. And so we can apply that to this, and we will get that this whole thing is equal to the cosine of arctan of 12 over 5 times the cosine of the arc sine of 3 over 5 minus the sine of arctan of 12 over 5 times the sine of arc sine of 3 over 5. It's a lot of writing. So one thing you may notice straight away is we have sine and arc sine. So those are actually going to nicely cancel out, and this whole term is going to be equal to just 3 over 5, right? Sine of the arc sine of anything just returns what that is. So this is just going to simplify to 3/5. But these other three, we are going to have to do some work on them. So I'm going to give myself a little room here and rewrite this up here a bit smaller. So we have cos of arctan of 12 over 5 times the cos of arc sine of 3 over 5 minus the sine of arctan of 12 over 5, and then this one we already know just turns into 3/5. So now let's start interpreting things. Okay, so arctan, again, takes as its input a ratio of side lengths of a triangle. So the triangle it is talking about has two legs of length 12 and 5. I know that it's the legs and not a leg and a hypotenuse because tangent only talks about the legs. Specifically, it talks about the opposite over adjacent. So if I draw the triangle that arctan of 12 over 5 is talking about, and I call this angle theta, then the opposite side from theta has to be 12, and the adjacent side of theta has to be 5. And this is just because when we have tangent of theta, it would be 12 over 5. So the arctan of 12 over 5 is theta, and it describes this triangle. We can then easily find what the hypotenuse is by doing, if we call this c, then c squared is equal to 12 squared plus 5 squared, which is 144, plus 25, which is 169, or, oh, sorry, not square root. This is 13 squared. So c squared is 13 squared, so c is 13. Now, from this, we can start to look at each of these places where we see the arctan, and then we say, all right, this arctan is talking about this angle, whatever it may be. And then I'm saying what is the cosine of that angle. And the cosine is going to be the adjacent over hypotenuse. So this entire term actually just turns into 5 over 13. Because the arctan of 12 over 5 is talking about a triangle that looks like this, and then the cosine of that angle is also referencing this triangle, and we don't ever need to know exactly what theta is. Likewise, over here with the sine of arctan of 12 over 5, well, we can look at what is the sine of this angle, and the sine of this angle is going to be 12 over 13, opposite over hypotenuse. So by constructing this one triangle, we're able to knock both of these things out. And then for the next one, the final one, we just need to translate arcsine of 3 over 5. So sine is opposite over hypotenuse, so arcsine is taking as its input the ratio 3 over 5, which means 3 has to be the opposite side, and 5 has to be the hypotenuse. If we call that side theta. So arcsine of 3/5 is saying what is this angle. And we don't actually need to know what that angle is, we just need to know what the triangle looks like. So if we have 3 and 5, then this side, we might already remember from the last time that the 3, 4, 5 right triangle is a really common one. And in fact, since we have 5 as the hypotenuse, that means this has to be 4. But you could also figure it out using Pythagoras. So now we know all 3 side lengths of this triangle. So when we say what is the cosine of arcsine of 3/5, what we're saying is what is the cosine of this angle, and cosine is adjacent over hypotenuse. So this is 4/5. I'd encourage you to go back and watch this a couple of times until you fully understand where these triangles are coming from and if you could on your own produce them from something similar. But then we have all 4 terms are now solved for, so this whole thing turns into 5 over 13 times 4 over 5 minus, because again we have a minus sign right here, 12 over 13 times 3 over 5. And so you may notice that there's a 5 here and a 5 here, and in fact they do cancel. But because we are doing a difference of fractions, we still need a common denominator. So I'm not going to do that cancellation. Instead, I'm going to say this becomes 5 times 4 is 20, 13 times 5 is 65, and then over here we have minus 12 times 3 is 36, and 13 times 5 is still 65. Now they have the same denominator, and this is going to be negative 16 over 65. Which is the correct answer. That's a lot. And basically, more of the same is effectively all section 4.8 wanted to talk about. So from here till the end, this is 4.9. So these definitions of the inverse trig functions are very, very powerful in their ability to do things, because now you can say, well, here's side lengths, give me an angle. Whereas before, you could only say, here's an angle, or rather, here are the side lengths. No. Yeah. One is the opposite of the other, and one of them's easy and the other one's hard. And depending on the type of problem you're doing, it may flip-flop which one you want to use. So understanding arcsine, arccosine, and arctangent is important, not just for solving wacky, contrived problems like this, but for instance, if you have to find the distance between you and something else and all you have is a flagpole. It might be useful to know your trigonometry at that point if maybe it's not contrived, maybe you actually do need to do something important. I'm not going to promise that that's going to come up in your everyday life, but you will have a better understanding of everything in your life if you understand trigonometry. Okay, so this is 4.9, and this is where we are now starting to talk about two different formulas. So 4.7, I kind of inundated you with a ton of different trig identities, like the Pythagorean identities, the sum of angle identities, the half angle identities, the double angle identities. There's even more, but just for our purposes, we really only needed those that I just said right now, but those only work when you have right triangles. So what do you do if you have something which is not a right triangle? And that actually looks like it might be by accident. So let's make sure that it is definitely not a right triangle. So if we label these sides A, B, and C, and then we label the angle opposite from A. So here's side A, and here's the angle opposite A. If we label this alpha, or capital A, or A sub 1, or A star, or whatever you want to call it, just so that you know that the pair alpha and A go together. And if we label the angle opposite B as beta, and the angle opposite side length C as gamma, because the Greeks don't have a C, then we can start to say things about this triangle. The book goes into a very nice derivation of why the law of cosine is true, but for us, all we really need to know is its definition. So the law of cosine states, it's essentially like the Pythagorean theorem, but adjusted and corrected to be used on non-right triangles. So this says a squared is going to equal b squared plus c squared. So far, that's just the Pythagorean theorem, but with the correction term 2bc and cos alpha. And the reason why it's cos alpha is because it's a squared over here. However, there are a total of 3 of these formulas, one for each side. So we also have b squared is equal to a squared plus c squared minus 2 ac cos. And now, because it's b over here, we have cos beta. And the last one, you might already pick up the pattern. It's c equals a squared plus b squared minus 2ab times the cosine of gamma, the angle opposite of c. Yeah, you can see all those. Okay. These 3 things together are the law of cosine. And it is not as easy to remember as the Pythagorean theorem. It's also not as easy to remember as the law of sine, which we are going to do in a minute. But these are also very powerful because, like I said, this does not have to be a right triangle for this to work. In fact, if it is a right triangle, then for whichever one of these is opposite the 90-degree mark, the cosine of 90 degrees is 0. So this whole corrective term goes away, and you're left with just the standard Pythagorean theorem. But let's do an example that helps us see why we might want to remember these. So if a triangle has side lengths, what did I do, 5 and 6? 5 and 6, with the angle between them of, what did I do? 135 degrees. What is the, well, I'm not going to write it, but what is the other side length, right? We have 5 and 6, and the angle between them is 135 degrees, so what is the remaining angle? I kind of regret writing this out because I need more space. So instead, I'll just sort of do this graphically and say this side length is 5, this side length is 6, this angle is 135 degrees, so solved for x. And we can do this using the law of cosines pretty easily. That, by the way, is supposed to be a dotted line, not just a lazy line. Yeah, so the first step, obviously, is that's given in degrees. We need to then radians. So if we remember, 135 degrees is the same as 3 pi over 4. And you can use the same things that we normally do, like we do 135 divided by 360, and then we take that ratio and multiply by 2 pi to get the answer, or you could look it up on a unit circle, or you could break this down and say, well, I know 135 degrees is the same as 45 degrees times 3, right? 45, 90, and then 135. So this should be 3 times what the radians for 45 degree is, which is pi over 4. So however you get to it, 135 degrees is the same as 3 pi over 4 radians. And so now we can use the law of cosine. So we know this, and we know this, and we know the angle between them. So the way we would use the law of cosine is we would say that x squared is going to be 5 squared plus 6 squared minus 2 times 5 times 6, all times the cosine of the angle opposite x, which is this one. And that's why I set it up the way I did. So this is the cosine of 3 pi over 4. Now we start evaluating things. So x squared is, well, 5 squared is 25, 6 squared is 36, 2 times 5 times 6 is going to be 60, and the cosine of 3 pi over 4 is going to be negative root 2 over 2. Right, if we have the unit circle, this is the angle 3 pi over 4, and the x coordinate here is the same as the x coordinate here for the regular pi over 4, but negative because it's on the other side of the x-axis. So it's negative. And now I can take this negative and pull it out and make that positive. So now we can evaluate, and we get x squared is equal to, well, 25 plus 36 is 61, plus 60 divided by 2 is 30, so I'm just going to have 30 times the square root of 2. And now we have to take the square root of this. So x is going to be the square root of 61 plus 30 times the square root of 2. I think in the notes I don't actually go that far. I think I messed up. Yeah, I mess up and don't take the square root. But, I mean, like, you might notice it and just scoff at me and my stupidity. But, yeah. So that's how you would use the law of cosine to solve a problem like this, where you're given 2 side lengths and an angle between them. And you can use the law of cosine to solve for the remaining side length pretty easily. This next one is also going to use the law of cosine, but it is going to, well, illustrate a couple of things. So firstly, we have, again, I'm not going to write it down, I'm just going to say we have side lengths 3 and 15, and this angle is given to us as pi over 6, which we should know is the same as 30 degrees. However, this triangle, again, while that may look like it's close to 90 degrees, it's not. It's just an arbitrary triangle with that side length, and this angle. But what we should notice is this differs from the previous one because the angle is not the one between the two known side lengths. It's actually just sort of one of the other two. So how do we solve this one? Well, we still need to use one of the 3 law of cosine equations, and we need it to have the cosine of pi over 6. That's going to correspond to having 3 out in front. So this is going to be 3 squared is equal to 15 squared, and if we call this other side x, plus x squared minus 2 times 15 times x times the cosine of the angle opposite the side length of 3, which is pi over 6. And I have to set it up this way because I don't have the angle between the two known side lengths, so I have to do some algebra. So we can start simplifying. So this is 9, this is 225, this is still just x squared. We have 2 times 15, which is 30, times x. So we have negative 30x, and then the cosine of pi over 6 is 1/2, which again we can look up on the unit circle, or we can figure it out using an equilateral triangle. So this is going to be 1 over 2. So we get that the 2 can cancel with the 30 a bit, and we get a simplified expression like so. Now we have constants, an x squared, and a multiple of x. So there should be some tiny alarm going off in the back of your brain that says, you know, it's a quadratic equation. To solve this x, we should use quadratic stuff. And in fact, we are. So we can rearrange stuff to get that x squared minus 15x. And then here we have to bring the 9 over. So 225 minus 9 is 216 equals 0. And now this is a perfectly fine quadratic equation that we can solve in a number of ways. I'm going to, how am I going to do this? I guess I'll do it here, as long as everyone can see it. Yeah, okay. So when we do this, we just apply the Pythagorean theorem to get negative b. So b is negative 15, so negative 15 is just positive 15, plus or minus the square root of b squared. So negative 15 squared is going to be the same as 15 squared, which was 225. Oh, sorry. That's why. All right, so the cosine of pi over 6, I had that right. What I didn't have right is that it's not 1/2, it is root 3 over 2. So this would have been minus 30x times root 3 over 2. The 2 is still going to cancel to give us a 15, but now we also have root 3. So I'm sorry about that. I did completely fub that part of the equation. All right, so it changes almost nothing, but it changes a ton of things. So when we do negative b, it's now not just 15, it's 15 times root 3, plus or minus, and now the square root, when we do b squared, it's going to be negative 15 root 3 squared, which is going to be the same as 225 times 3, or 675. Obviously, I didn't do that in my head, I just have done this before, so yeah. Then we have to subtract 4 times a times c. So in this case, a is 1 and c is 216. So when we do 216, and then we have all over 2a, again, a is just 1, so this is all over 2. However, we are about to run into a fairly significant problem. This is the same as 15 root 3 plus or minus the square root of negative 189 all over 2. Emphasis on that is a negative number. And the last time I checked, this wasn't a complex analysis class, so for us, there is no such thing as the square root of a negative number. So something's wrong. But, you know, don't worry, this is not, this doesn't show that the law of cosine is wrong. Instead, it shows that the triangle I have described cannot exist, right? This situation cannot exist. And one way to illustrate why is exactly this, because we wind up getting an imaginary answer. But another way is to draw this out accurately. So in the little image I placed in the notes, I did this on Desmos. And basically all I did was say, I know that if this is my angle of pi over 6, and I set this length to be exactly 15, if I place a ball or a circle on this with radius 3, then if this were ever going to build a triangle, then this line and this circle have to intersect somewhere so that I can have a length of 3 that reaches the other line. However, when you actually go and do this, like I did in Desmos, you find that there is a fairly appreciable gap between them. And so stating that there is a triangle with side length 15, 3, and an angle pi over 6 right here doesn't actually work. That is not describing an actual triangle. So if something like this happens while you're doing something, bear in mind the answer may be that it's a trick question. And in fact, that's how I would label this question, is it's a trick question, because it's assuming a triangle which cannot exist. So you're either going to get imaginary distances, or you should conclude that the triangle doesn't exist, which is the correct answer. Law of cosines are fairly easy, so I'm not going to do any more examples. In fact, I don't do any more in the notes either. But if we keep this exact same example, we can now talk about a different way to find that it is an impossible triangle, and this is going to be using the law of sine. So I'm going to draw a triangle again. I don't know why mine always look like they're right triangles, but they're not. So if we call this A, this B, this C, just like before, we're going to call this angle alpha, this angle beta, and this angle gamma, because beta is opposite B, alpha is opposite A, and gamma is not in our alphabet. But if we have this situation, the law of sine, technically the law of sines, says that the sine of alpha divided by A, right? So the sine of this angle divided by the length of the opposite side is equal to the sine of beta divided by B. So the sine of this angle divided by the length of the opposite side is also equal to the sine of gamma over C. So this is the law of sine. It basically says that the sine of this angle divided by this length, or the sine of this angle divided by this length, or the sine of this angle divided by this length are all the same number. It's sort of an invariant constant for a triangle. And if we use this identity, this rule on the previous example, then we get, so if we use this exact thing on the previous example, then we have, so just to substitute some things in, we know that A was 3, B was 15, and alpha, the one that was opposite 3, was pi over 6. So we were trying to find the length of side C. Last time we tried using the law of cosines, and right now we're going to use the law of sine, and it's also going to show us that it's impossible. So the way we do this is we say sine of pi over 6 over 3 is going to equal the sine of beta over 15, which is going to equal the sine of gamma over C, our mystery side length. This, we actually know what it is. The sine of pi over 6 is 1/2. So this is going to be 1/2 over 3, which is the same as 1/6. And so 1/6 is equal to sine of beta over 15, which is equal to the sine of gamma over C. And the thing I'm going to do is we're actually not going to find an issue when we try to solve for C, but if we try to solve for sine of beta, potentially trying to figure out what angle beta is, this is where we're going to have our contradiction. So, using just this relationship, I can say that sine of beta is going to equal 15 over 6, just by multiplying both by 15. However, 15 over 6 is 2.5. Okay, what does that mean? That's a problem because we know that sine is bound between -1 and 1. There, in fact, is no angle beta that will give us a sine of 2.5. It just doesn't exist. And this is where we find that contradiction. Because the sine of beta is too big, the angle beta cannot exist. And it's sort of, this part here is like on the diagram I had before, that's where the gap was. So it's describing the exact same problem, but this time through the law of sine. I'm only going to do one more example, but this one's kind of a doozy. So the next one is going to be, all right, we say that, I'm just going to draw the triangle. So it says we have a triangle. Dang it, they always look like they're right triangles. So I'll do, is that big enough? That might not be big enough. All right, so we know that we have a side length of 2 as given in the prompt, and the angle opposite that is pi over 4, so that'll be this angle, and then we know that one of the other 2 angles is, where does it say? It is pi over 3. So let's just say it's this one. This one is pi over 3. And you might think, well, couldn't it be that one? It's fine. Like the symmetry of this means that no matter which one I say, the triangle is just going to be the same triangle. It might just be a mirror image of itself, but it'll still have all the same answers. So the question is, what are all 3 angles and what are all 3 side lengths? You're only given 2 angles and 1 side length, and we can use the law of sine. We could also use the law of cosine, but we're going to use the law of sine to solve this. First thing is we know all angles must sum to pi, right? This is a triangle, and so we know that the internal angles of a triangle have to sum to 180 degrees, which in radians is pi. So we can already figure out all 3 angles fairly easily. To figure out what this angle is, we just need to take pi minus the other 2. So minus pi over 4 minus pi over 3. And when we do this, we can combine these into, this is pi minus pi over 3 plus pi over 4, just by factoring out the negative. We know what this number is because we dealt with it last time. This is the same as pi minus 7 pi over 12. And so now to solve this, we have to write pi as something over 12. So this is going to be the same as 12 pi over 12 minus 7 pi over 12, which is 5 pi over 12. So we can actually solve for this angle, 5 pi over 12, and we've already actually answered half of the problem, which is what are the 3 angles. However, that's obviously the easy part, so now we have to do the hard part. The hard part happens when we say, all right, let's call this B and this C. So let's try to solve for side length B. So we're going to use that 2 and pi over 4 have the relationship sine of pi over 4 over 2 should equal, and now it should be the sine of pi over 3 divided by the side length opposite it, which is B. This stuff we can figure out perfectly well. We know how to do those. So what is sine of pi over 4? It is, it is root 2 over 2, which is going to be root 2 over 4. And this is going to equal, what is the sine of pi over 3? Well, sine of pi over 3 is root 3 over 2 over b, which is going to be root 3 over 2b. So we have this is equal to this, and so we can just solve for b. We get that b is equal to root 6. If you want to follow the algebra of that, there's more of it in the notes. So we know that b is equal to root 6, which is great, because now we can solve for side length c. And we're going to do this in exactly the same manner. We know that sine of pi over 4 over 2 is going to be equal to the sine of the angle opposite of side C, which we found is 5 pi over 12. So this is 5 pi over 12 all over C. And we know what this one is equal to. We just did it. This one is root 2 over 4. So now let's try to see if we can solve for C. We can solve for C by multiplying by C on both sides to get C, root 2 over 4 is equal to sine of 5 pi over 12, and then we can divide by root 2 over 4 to get C is going to be equal to 4 times the sine of 5 pi over 12 all over root 2. And yes, there's a way to cancel these because this has a total of 8 square roots of 2 in it, but I'm not going to do that. Instead, I'm going to, as the proverbial mathematician always says, leave it as an exercise to figure out exactly what sine of 5 pi over 12 is. I'm just going to say that I found it using the exact same techniques that I did in the last notes, where I first found that 5 pi over 12 is pi minus 7 pi over 12, and then I used the angle sum formula. Get off my foot. So this turns out to be the sine of 5 pi over 12 equals, and what was it? It was root 6 plus root 2 all over 2. So using, I don't think you can see that, good. So root 6 plus root 2 all over 2 gets plugged into this, and it simplifies everything out to be C is equal to, I'll do it up here, C is equal to root 3 plus 1. And so we are done. We found all 3 angles, and we found all 3 side lengths using just what was in the prompt. So that's it for chapter 4. There is more material in the book. A lot of it's more like special case stuff, or like, hey, you might want to know this for this type of problem. But for us, that is broad strokes trigonometry. So I would advise you to go through the notes multiple times. I would also advise you to go through the book, because that's where I'm getting this. And yeah, I think that's it.